Thank you so much for this kind introduction. Thank you all for coming. It's always great to be here at Stanford to learn about all the exciting research that is happening here. I actually didn't come all the way from Zurich. I'm spending some time in Cambridge right now, in Boston on the East Coast. I'd love to share some work that we've been doing in a group around safe and efficient learning in the real world. And of course, this is joint work with a fabulous group of PhD students, postdocs, and senior collaborators who I'll acknowledge as we go along. So you probably all agree that these are really exciting times for machine learning and artificial intelligence. Sort of far beyond classifying images, translating languages, these models now really exhibit a pretty impressive level of generality. You can ask them to compose poems about and rap songs around submodular optimization, right? There's examples of creating photorealistic videos from textual descriptions and the like. So this is certainly super exciting. What does it take to sort of bring these advances to the physical world, right? Applications like human-robot interaction, advancing recommendations in healthcare, scientific discovery, precision farming, and the likes, right? So as soon as you sort of talk about the real world, stakes are high, right? Failures are much more problematic. And so what we've been really interested in is how can one enable learning agents to actually learn by interacting in the real world. And I want to share some of the thoughts that we've been exploring in this space. Now, the central paradigm in machine learning in these contexts is reinforcement learning, which of course this is an abstract model of an agent that's situated in an environment which it can affect by carrying out actions that cause the environment to change its state in a Markovian fashion and the agent to derive some reward. Right? And of course, the same model has been studied in controls, so adaptive control, approximate dynamic programming, and the likes. And a key challenge in this domain is that the agent doesn't know how the world works. So it faces the dilemma of trading exploration, so experimenting with actions to learn about their consequences, and exploitation using what it learned in order to do well. Okay, and so we've also seen these pretty remarkable advances a few years back in gameplay, but also more recently in challenging robotics applications, like our colleagues in Zurich, for example, use them to have robots go hike, right, or fly drones faster than human pilots and so on. So it's certainly pretty exciting advances in this space. Now, RL is sort of portrayed in this cartoon that the agent goes out and learns by interacting with the real world. But of course, in truth, the agent lives in a matrix, right? So the agent really needs an accurate simulator that describes how the world works. And a lot of applications that, like those that I've mentioned before, there's at best approximate simulators of how the real world would work, right? In applications like scientific discovery, you do quite a bit of work sort of around self-driving labs and autonomous experimentation. And so, I mean, that's the whole purpose of science, to learn kind of how the world works. And so the question is, now, if you go to these domains, then exploration, right, is costly. You need to carry out experiments, so you really want to be sample efficient, and potentially dangerous, right? And so we've been really interested in how can learning agents learn by interacting with the real world efficiently and safely. And that's what I want to talk a little bit about in this presentation. So I'll start with a line of work that we've been pursuing now for a couple of years around safe Bayesian optimization, and then build on that to talk about sort of some recent directions that we're exploring. And so let me start with the motivating example. So this is a collaboration with the Paul Scherrer Institute, a large research facility in Switzerland. This is the SwissFEL Free Electron Laser. It's a 700-meter-long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second. So you can use this to image very fast processes like molecules turning each other in the context of a chemical reaction, super important applications from drug design to materials discovery to many others. It's also a pretty complicated device. So the beam properties are depend on a carefully arranged set of magnets that partly actually are physically moved around. The beam properties vary quite substantially based on subtle environmental conditions like temperature, humidity, have to be adapted based on target application requirements and so on. So it's not just that you set this up once and you're done, but you have to constantly sort of adapt it. It's also safety critical. So if you're not careful what you do, you can basically damage the machine, right? Damage the magnets and destroy it. So really have to be careful. But fortunately, of course, there's monitors all over this device, right? That sort of monitor how close you get in terms of violating some of the constraints. There's another question is kind of, so maybe the other thing I want to mention is, so in principle, we can simulate the underlying physics. But the simulations are extremely expensive at this level of accuracy. And given the fact that you really need to adapt to different environmental conditions and so on, you can't really run and prepare this in simulation. Okay, so essentially you have to do this tuning and experimentation on the device while it's running. And so one way to sort of think about this very abstractly as sort of trying to optimize a black box, right, this electron laser, by injecting some tuning parameters, theta t over time, and obtaining some measurements about the rewards, right, namely beam intensity, say, so other targets you care about, as well as sort of how close you are to violating some of the constraints, right, through these beam loss monitors. Right? Given this information, you'd like to close the loop. The problem is you don't know the reward nor the constraints ahead of time, right? You really need to take your observations into account in order to drive experimentation. So in a way, what you want to do is you want to solve sort of this nonlinear constraint optimization problem, optimizing this unknown reward subject to unknown constraints while maintaining feasibility every step along the way. And of course, in general, this is a completely ill-posed problem, right? Without any sort of prior assumptions, this is hopeless. So one way to impose prior assumptions is to kind of take a Bayesian perspective on this and try to model uncertainty in the unknown objectives and the unknown constraints. And that's exactly sort of the philosophy behind Bayesian optimization, right, where one endows the unknown reward and constraint with a stochastic process prior, which one can then use in order to guide experimentation while being cautious. And so kind of the first result we had about this a while back is basically operationalizing this idea. So we model the reward and constraints in a way as samples of the probabilistic model. So kind of a classical default in Bayesian optimization is Gaussian process models that we analyze quite a bit. You can also use Bayesian neural network models, and we'll talk a little bit more about kind of neural network-based approaches later. And then you can use the uncertainty to, on one side, reason about constraint satisfaction. So for example, if you use a pessimistic estimate of your constraints, right, the lower confidence bound about the constraint, right, you can sort of statistically inner approximate the feasible region, right, that holds with high probability as long as these models are well calibrated. And similarly, you can use kind of your confidence estimates about the rewards in order to, for example, reason about what are subsets of the parameter space that are plausibly optimal, right, where kind of the optimistic estimate exceeds the best as a pessimistic lower bound. Right? And so a natural kind of algorithm would be to basically try to explore within kind of this plausibly optimal region, but being constrained in this red set, right, this feasible region. The problem is that then you quickly get stuck in suboptimal solutions. So what you also have to be careful about is, in a way, to sort of try to gather information about what is feasible in the first place. And that's captured using this notion of expanders, of course, everything mathematically defined in the paper, where you sort of have an incentive to actually try to explore the boundary, right, and discover new regions in the space that you can statistically certify to be safe. Okay, and eventually you might find better solutions this way. That's sort of the cartoon picture, right? Of course, the details are in the paper. But in order to kind of make ideas like this work, you really need these models to be well calibrated. So you need to make sure that this true unknown objective and true unknown constraint are actually contained within the credible sets of the Bayesian model. There's also similarly kind of frequentist perspectives on this. And so now, of course, if you kind of were a Bayesian, you had a perfectly well-calibrated model. You could just take a point, take your mean, add some multiple times your standard deviation, and enumerate kind of your percentiles on that marginal distribution. But of course, your model might be miscalibrated, right? The true objective might lie outside of these credible sets. And moreover, you want to ensure that these bounds hold actually everywhere in the domain and uniformly over time. And that's sort of constructing models that produce these kind of well-calibrated confidence sets that hold reliably uniformly over time, sort of are in time valid. That's a very interesting, important sort of theoretical question. And we've been spending quite a bit of time sort of looking at these types of problems. And it turns out it's actually possible to calibrate these uncertainty sets. So you need to, in a way, take into account kind of the mismatch between the underlying objective and these confidence sets, as well as some notion of capacity, right, that in a way you can use in order to get uniform bounds over the domain. So there's quite a bit of work on the statistical side that I'm not going to dwell on too much in this talk, on sort of trying to really understand in what sort of circumstances you can analyze this. So the first works were around Gaussian process models and can extend this to some extent to neural network-based models and other models as well, and also other types of likelihoods. And now, under these types of regularity conditions, regularity assumptions, one can actually analyze this algorithm that I've described to you before and establish bounds on how many samples you need in order to find a near-optimal reachable solution while ensuring constraint satisfaction with high probability every step along the way. Okay, and so variants of this algorithm we actually got to deploy on this real device. So here's a picture of my student Johannes And Moimir, together with our collaborator Nicole, is sitting in the operating room of this machine, running the code in the background. And they would do experiments that they would start with parameter settings that were chosen by the domain experts, kind of detune them so that the whole system would perform badly, and then try to recover, right, using different strategies, right? And so there's kind of local search-based strategies that are used in this domain, and you can actually do quite a bit better by the sort of more global optimization that safe Bayesian optimization affords, and at the same time actually have these safety guarantees. And this is kind of an early work. There's been now quite a bit of applications of kind of the safe Bayesian optimization machinery. So we've did another collaboration kind of around kind of large-scale scientific instruments. This is a high-intensity proton accelerator operated by that same research center. That's even more safety critical in some sense. So you really have to be careful about what happens. And here, the system really allows you to actually find much better solutions without kind of generating beam interruptions. We've been using this to tune gain parameters for high-precision motors used for industrial manufacturing tasks, tune control gate parameters for quadruped robots, and the likes. And so now what I want to do in sort of the remainder of this talk is to kind of tell you about some ideas towards scaling these ideas to sort of richer and more complex applications. And so one first topic that I want to talk a little bit about is sort of where kind of does the prior come from? Right? So in Bayesian optimization, really the key requirement is you need a probabilistic model, right? That sort of encodes your prior assumptions about how the unknown objective and rewards looks like. And if there's one thing, right, to learn from all the advances in deep learning and now also in generative AI, it's really that if you have enough data, kind of learning good representations, you can often do better than hand-designed representations, right? And so in addition, right, once you learn good representations from one task, often you can adapt it or fine-tune it to related tasks, right? Like for example, take image classification models trained on natural images, and just using a little bit of, say, medical data, you can sort of adapt the model in a very simple, efficient manner. So the question is, can you do something like this for sequential decision-making tasks like Bayesian optimization? Okay, and so there's a very natural perspective on this, right? Through the lens of Bayesian meta-learning. There's also some really interesting work that's happening here at Stanford, sort of in this domain, where you, instead of starting with a hand-designed prior distribution, right? Maybe a Gaussian process prior with a fixed kernel that you choose, to step up one level in the Bayesian hierarchy to take a collection of tasks, right, from related domains, and then try to, starting with the hyperprior on the parameters of your prior distribution, apply Bayesian inference or approximations to obtain a hyperposterior that in a way absorbs all the information from related tasks, and that you can hopefully adapt in a very simple, efficient manner to new tasks. Right? So that's a classical idea. The question is sort of how to get this to work with modern models. And so the canonical approach of how to address this is to basically start with the hyperprior on the parameters of your prior distribution. Okay? And so you can do this, for example, for shared linear regression, right? Maybe you have different linear models. There's sort of a common set of coefficients across all tasks, and then kind of you learn how to deviate sort of across different tasks that you want to fit. The question is how to do this in sort of this basically non-parametric setting involving neural nets. And now the default choice that's often done in the literature is to start with a very uninformed kind of isotropic prior. Just put a Gaussian maybe on the coefficients, the weights of the neural network. The problem with this is it's kind of very hard to reason about what kind of prior assumption this really imposes on this function space. And you also get often very poor kind of empirical side effects if you do something like this. And so what we've been exploring as an alternative is to in a way encode prior assumptions directly on the space of functions. And the motivation in a way is the Gaussian processes behave in kind of a very interpretable fashion. So what typically happens is close to your data, you're confident, and as you go away from your data, your uncertainty goes up. The question is, how can I express these types of prior assumptions in this context of Bayesian meta-learning with neural network models? And so that suggests kind of a very natural perspective towards meta-learning, basically trying to kind of learn a model of this underlying stochastic process directly that governs the spatial reward function and constraints. Now, that seems like an even harder problem, right? You start with the problem of specifying a prior over a large but finite set of parameters. Now you want to learn a prior distribution of entire functions. But fortunately, stochastic processes are fully defined on their marginals. So you really only need to characterize them where you use them in some sense. And moreover, you don't actually need to learn the full underlying prior distribution of our functions. So it turns out sort of all the standard approximate inference techniques for Bayesian deep learning, all they really need is what's called the score. So the gradient of the log density of this stochastic process prior on a set of points where you evaluate them. So as long as you can sort of get your hands on that score, you're in business. And that's the perspective that we've been exploring. So essentially what you want to do is to take a bag of tasks, right? Maybe observations in past tuning sessions with this free electron laser, to stay with this running example, and then sort of try to learn something about this underlying stochastic process prior. Okay, and so what he said is we really need to control the marginals of this underlying stochastic process. Right? So the one-dimensional marginals, of course, are just the function responses, say at a particular point x. Right? So this is one example. And of course, we can look at higher dimensional marginals, like a two-dimensional example of x point, basically the function response at points x1 and x2, and how they're jointly distributed. For Gaussian processes, all these marginals are Gaussian, right? Joint Gaussian, that's a characterizing property. But in general, of course, they need not be. And so the question is, how can we sort of learn a flexible model that in a way allows us to predict enough about sort of the score where we want to use these models to make predictions? Okay, and so to this end, we use a very flexible neural architecture, basically a transformer-based model that sort of directly seeks to predict the score of where we use it for the stochastic process prior. And in order to predict the score, we basically use score matching, right? So we kind of the key machinery used behind diffusion models. Okay, and so that actually works really quite well. So in the ICLEAR paper last year, we do a fairly extensive empirical study, goes to a whole range of different data sets, ablation sequence, a whole range of different meta-learning and not meta-learning based approaches. Some of them really designed for Bayesian meta-learning and asserting quantification, some for constructing point estimates, and really stress test them in kind of this regime where you have very few examples per task and possibly also only very few tasks, right? Sort of this really challenging domain where you really need to extract as many bits as you can from related observations. And so there's one data set is about this free electron laser example that I mentioned, right? So here tasks correspond to different tuning sessions. There's a medical time series data set we look at. So each task is a patient monitored in the intensive care unit. You want to learn a joint model that in a way explains all the data, but personalize it with respect to each patient. There's a whole bunch of other data sets we look at in this context as well. And this model performs really quite well in terms of the flexibility, both in terms of getting high accuracy and also getting low calibration error. Now, of course, there are lots of interesting theoretical questions of what one can do about meta-learning probabilistic models, in particular for sequential decision making, where you don't get IED data. In general, it's a very hard problem. I just want to give a quick shout out to my student Panyan, who's been looking at more theoretical questions and more parametric regimes of this question. So analyzing this algorithm end to end, I think, is quite challenging. Now, one thing I want to talk about is sort of how does this interface with tasks where safety is important, right? Where you really not just want to get good prediction, but you really want to make sure that you produce conservative uncertainty estimates. And so there, what we've been looking at is basically encoding a little bit more structure in terms of this hyperprior. And so one way to do so is to use the Gaussian process as sort of a hyperprior, and then basically shaping it through sort of key hyperparameters. So one key parameter is basically kind of the scale parameter, the variance of the function responses. Another key parameter, of course, is the length scale, right? And if you sort of have large length scales, single observations in a way reduce the uncertainty a lot, right? So this is associated with getting a lot of information, but of course might be unsafe, right? If you in a way sort of predict too large of a reduction of uncertainty. In contrast, small length scales are much more conservative, but of course might lead to more robust behavior. And so you can sort of look at this kind of basically phase diagram here in some sense, right, where you compare these hyperparameters along length scales and the variance, right? And in a way, if you decrease length scale and increase the variance parameter, right, the model becomes more conservative, but of course correspondingly slower. If you increase the length scale but decrease the variance, you get unsafe behavior. Okay, and so now the question is, of course, how do you find the sweet spot? And so ideally what you'd like to do is you'd like to find such parameter settings such that in a way, you ensure constraint satisfaction sort of during learning, while at the same time minimizing regret, so maximizing performance at the corresponding task that you would want to run. And of course, that you can't really do in the absence of actually collecting data and deploying the algorithm. And so what you show in the scroll paper is that it's possible to sort of find computationally efficient proxies for these metrics that you actually care about. Okay, in particular, what you can look at is on related tasks, what's the calibration of the model, so in a way the coverage of the corresponding confidence sets that you get out of this model. At the same time, you can also look at, in a way, the efficiency of the prior, so the amount of reduction in variance. Okay, and so these are very correlated across these different tasks. And you can use this idea in order to basically do some sort of frontier search algorithm, to in a way solve this constraint optimization problem that you in a way maximize the informativeness of the prior while ensuring calibration on past data sets. Okay, and so that's in a way is basically a very compact parameterization of this hyperprior that sort of shapes your stochastic process predictions that you can then navigate efficiently experimentally. We've done a fairly extensive study, including experiments on hardware experiments where basically using these meta-learning ideas, not only you get sort of conservative predictions, which is what you would want, but you get substantial acceleration in terms of performance. So if you don't use meta-learning, in a way you take much, much longer in order to find good parameter settings than using this correspondingly optimized prior. Okay, so this is some of the work that we wanted to talk about meta-learning, so reusing information from related tasks. And now the question is, how can we make use of it in tasks beyond Bayesian optimization? What I want to talk a little bit about is how to lift ideas from Bayesian optimization to learning-based control, in particular sort of Bayesian model-based reinforcement learning. And so Bayesian optimization is really sort of a black box method, right? You in a way have this black box, you put in a parameter, you measure something as an output. Right? But in sort of dynamical systems, you really would want to make use of observations of how the system actually works, right? State observations along the way. Okay, and so one way to sort of think about this is to basically model an unknown dynamical system, right? Governed by basically a Markov transition kernel. In the illustrations here, we'll actually talk about deterministic systems, but you can scale these ideas to stochastic systems as well. And what we're going to do is you're basically quantifying uncertainty in the dynamics of this dynamical system. Okay, so these confidence sets that we talked about before, so they basically govern the transition kernel, right? Our epistemic uncertainty about the next state, st plus 1, that you would get to if you carry out action AT in state st. Okay, now you can sort of think about this way, right? Suppose you want to start from some starting state, maybe go to some goal state while avoiding unsafe states. What you can do is you can basically propagate sort of the epistemic uncertainty in this unknown dynamics model. But since you're uncertain about where you end up, right, you can't, right? You don't really know where you actually will up when you carry out this policy. But of course, once you deploy it, you collect information, your uncertainty is going to contract, and you can sort of replan and hopefully be less conservative, right, and obtain improved behavior. Okay, and so what we can basically do is use these confidence sets both for reasoning about exploration, right? So you might want to think about planning an action sequence that will plausibly allow you to achieve the task, while always going to avoid visiting unsafe states, right? With respect to the confidence estimates afforded by this probabilistic model. Okay? And so the question is how to make this work with algorithms for reinforcement learning, right? And scale them to complex tasks and complex control policies. And so first, I'll just talk about kind of optimistic exploration. So how should we go about, in a way, using reinforcement learning for introspective planning, but being very careful about interactions with the real environment to kind of learn good behavior very quickly. Okay, and so the protocol we're going to look at is basically this model-based RL paradigm in the episodic setting, where every round we carry out an episode, we have a current policy, that we interact with the real environment. So we deploy it, we're going to collect data, and we use this data in order to refine our estimates of the transition kernel, of the dynamics model. And then we use the epistemic uncertainty around this transition model in order to replan our policy. And for ladder, that is a purely introspective task, right? So we basically use the estimates, including the epistemic estimates of the uncertainty, in order to basically plan a new policy. And this is where we want to make use of kind of state-of-the-art techniques in model-free reinforcement learning, policy gradient techniques, and so on, right? So in a way, we want to kind of estimate a simulator where we can spend computation, whatever you want, in order to find a good policy, but then be very careful when deploying it on the real system. Okay, so how would we do this? So one way of how one can think about doing this in model-based RL is to basically try to optimize our objective, and we discounted returns. I understand that's sort of approximate dynamic programming formulation. But the problem is we don't know really the transition kernel. So typically, right, you would assume you can actually at least sample from the transition kernel. We don't know what the transition model is. So what one can do is one can sort of consider an optimistic transition kernel, right? There's a set of plausible transition models, dynamics models, and try to optimize the policy that under its most plausible realization, you do well. Okay? So now the problem is, solving this optimization problem is really difficult in general if you have complex things like Gaussian process-based dynamics models, neural network-based dynamics models, and so on. You have a very complex, non-convex constraint set that you have to optimize over. And so as a consequence, sort of state-of-the-art techniques that use epistemic uncertainty about the unknown transition kernel typically just average out over it, right? Optimize over an expectation, for example. So this is at the heart of from the Pilko method, as a classical method for model-based RL with Gaussian processes, the PETS method using neural network ensembles, and so on. That's basically just average over your models, basically sort of certainty equivalent control in some sense. Okay, and so what we figured out is a way of actually carrying out optimistic exploration, so propagating the uncertainty in the dynamics model, but reducing this problem to just a standard approximate dynamic programming problem to which one can apply standard model-free, say, policy gradient algorithms for introspective planning. And let me just explain sort of how that roughly works. So here's a simple kind of one-dimensional cartoon. So suppose we start in our starting state, maybe S0, and we want to reach a sparse reward state. So the y-axis is kind of the one-dimensional state space in this cartoon. The x-axis is time. Okay, and so now for illustration again, let's just look at deterministic dynamics. So the only uncertainty is of epistemic nature, that we have lack of information about the consequences of our actions. So it means that if we consider a candidate policy, pi, that is going to take us to some kind of nominal next state, predicted next state, then we'll have some epistemic uncertainty of where we would really end up. Okay? And so in this formulation I talked about before, now you just have to do this for all plausible dynamics that you would unroll forward. So instead, what we're going to do is we'll let the agent control its luck. Okay? So we'll let the agent choose where within this one-step confidence sets it wants to end up with. Okay? So it can choose where within sort of these plausible next states it will be. Now this gives us a sort of optimistic next state, and basically using these uncertainty sets where you essentially describe kind of rectangular uncertainty sets, right? Maybe have a nominal next state prediction and some sort of coordinate-wise next sort of uncertainty estimates for the next state. You can basically reparameterize this choice as sort of a new dynamics model, F tilde, that in a way takes this control action that lets the agent control its luck into account. Okay, and so now we can sort of keep unrolling this further, get another optimistic next state, unroll it further, get another optimistic next state, and then finally reach this high reward state. And so what's nice about this is basically just a standard approximate dynamic programming problem to which one can apply standard policy gradient techniques in order to solve it. Right? And basically throw the hammer at it, right? That's kind of the matrix, right? That's the learned simulator in a way that you have to optimize, that in a way incorporates the epistemic uncertainty about it. Okay, so here's kind of a simple cartoon illustration on the sort of inverted pendulum task. So you want to swing up the pendulum. So here's start at the beginning, right? So the agent knows nothing about physics. only has some vague smoothness assumptions about the dynamics. And so the first optimistic trajectory just believes if I just push it in one direction, I can swing it up. And of course, that's not how the world works, right? So if you actually carry out that policy, the pendulum just swings down a little bit in the swung down position. Then, of course, you update your model, right? You quickly learn that you actually have to swing back in one direction in order to swing it up on the other direction. That still doesn't quite work, but now you collect relevant data over a large part of the state space. Condition on it, right? Now, just a little later, basically you learned how to swing it up, but it slightly overshoots, right? Because you haven't collected any data on the top. And then just a little later, it basically has found an optimal policy where sort of the optimistic estimate corresponds to the actual one observed. Okay, and so now, that's of course a very simple task, but apply this to kind of standard deep RL benchmark tasks. So here's comparisons against sort of this greedy, the certainty equivalent method, just averaging out over the uncertainty in a transition model. Also comparing against Thompson sampling, so posterior sampling, where you basically sample one of the models from the posterior. And here's this optimistic exploration, which already in this setting does maybe a little bit better. There's, of course, a lot of variability when training these reinforcement learning agents. We can make the problem harder by increasing sort of action penalties, right? Sort of typically would want to encourage the agent to use as little force as possible. Okay? And so if you do that, exploration actually becomes harder. And why is that? Well, standard policy gradients, if you penalize using large force, will essentially learn to do nothing, right? Will basically learn to sort of stand still. Okay? But with this reparameterization, you learn that there is actually a chance of sort of getting further if you just stick with it. Right? And eventually, kind of, you really need this optimistic in order to reach kind of sparse reward states. And here's just sort of a little cartoon illustration of this, right? So if you don't use action penalties and just use policy gradient techniques, you sort of just happen to learn how to move forward by vigorously waving with your extremities or so, right? So it's probably not exploration you would want to do in a real robot, right? And so if you kind of regularize by essentially controlling these action penalties, then the behaviors are maybe a little bit more constrained. Okay, but of course exploration becomes harder. And you can do similar ideas once you have constraints as well. So this was only about sort of efficient exploration. You can also be a bit more careful about reasoning about constraint satisfaction. For example, one can do the same idea sort of in constrained MDPs, which is one way of not just having a reward, but also having a cost that maybe quantifies the probability of visiting unsafe states. Right? That's one formalism that's been looked at in this context, where you want to sort of ensure constraint satisfaction. And now again, the trouble is that in standard constrained MDPs, you need to know what the transition model is. So you maybe need to be able to sample from it. Okay? But you can use that same kind of idea, but now you can sort of be optimistic with respect to exploration, but be pessimistic with respect to constraint satisfaction. Right? And use similar kind of reparameterization ideas in a way to turn this into a problem to which one can apply sort of the hammer, right? Standard deep RL policy gradient-based techniques for constraint policy optimization. Okay, and so there are some experiments that we describe in the iClear paper on sort of learning to control. I mean, this is relatively simple robotics tasks in this safety gym benchmark suite, sort of a point mass, some simple car model, kind of a simple quadruped, in order to solve tasks like reaching a goal, touching buttons, pushing a box to a goal, and the likes from a sort of first-person view. So there's a forward-facing camera. I tried to learn directly from pixels, and now basically use kind of a state space model to account for the partial observability and sort of do uncertainty quantification around that. But otherwise, the ideas are basically the same. Right? You can apply them to the constraint setting as well, right? And here's kind of just examples of the types of observations that the agents get to see in the tasks that is going to carry it out. Okay, and so there's a bunch of experiments where we compare this algorithm, this optimistic, pessimistic algorithm, with a bunch of other model-based and model-free deep RL algorithms, both along the final objective achieved at the task, how kind of the fraction of cases where you achieve constraint satisfaction at the end of the task, right, where you satisfy, really find a safe policy in the end, as well as safety during training. This is a very difficult task. You really learn from scratch by observation only from pixels, right? So essentially safe exploration is very difficult in that sort of setting, but at least you still want to kind of learn kind of as carefully as you can. And so basically across this comparison, this approach leads to good task completion, is the only one that's actually able to safely complete all these tasks, and also does pretty well, even not perfect, in terms of kind of the safe exploration objective. There's also comparisons against kind of model-free techniques that are given a lot more environment interactions, so orders of magnitude more environment interactions, and you sort of find similar performance in the end, but of course much more efficiently in terms of much fewer interactions with the actual environment. Okay, so that brings me to kind of the last part of the talk that I want to do in order to sort of combine some of the ideas we've been discussing throughout this presentation. And so here's kind of a simple illustration on a task of taking this race car, and what you want to do is you basically want to reverse park it. It's not a particularly complex task, but it's sort of nice example. It's non-trivial in the sense that there's slippage, right, and there's kind of properties of the tires, and so on. If you want to really carefully model this, it's challenging. And so we can first just run kind of this basic model-based RL algorithm that I've described to you before. And so after a couple episodes, so initially just sort of collects data. Again, it uses a completely uninformed dynamics model, so knows nothing about physics, right, and knows nothing about the environment. But after about 20 episodes or so, it roughly is able to learn the task, right? So certainly, I mean, model-free RL algorithms will use many orders of magnitude more samples in order to get there. So it's relatively sample efficient still to learn completely from scratch. And of course, maybe a much more standard way of trying to solve that problem, right, from controls engineering would be to maybe derive a first principle physics-based model, right, do sysID to estimate the parameters, then derive a feedback controller and deploy it on the system, right? That's maybe a much more sort of canonical strawman that one should compare with, right? And so now, of course, if you're careful with modeling, this works perfect, right? If you use a very simple kind of model, so here's basically we just use sort of a bicycle model, then there is, of course, a sim to real gap. So you won't exactly sort of solve the task. You'll get pretty close, but you won't exactly solve it. Of course, you could spend more work to kind of model tires, model slippage, and so on, right? But instead, we want to be more data-driven. And so the question we asked is kind of how can we get around sort of the sim to real gap kind of in a more data-efficient fashion? And so what we've been exploring is basically through this lens of Bayesian meta-learning. But instead of starting with a data set that's collected from a bunch of related tasks, we want to replace it with a simulator. Okay, so let's just use a very simple first principle simulator, right? Just the bicycle model with a bunch of sort of different parameters. And in a way, describe the underlying stochastic process, the prior assumptions of the dynamics model, through, in a way, a prior distribution over these different parameters that govern the simulator. Okay, and so now what you want to do is you basically want to learn a model sort of in a completely data-driven fashion, however, bias it or regularize it towards behaving sort of like the simulator does. That's sort of the idea. So we want to innovate to kind of distill, right, the simulator into a neural network prior. That's sort of the idea behind it. Okay, and so what you basically want to do is use the same idea that I've discussed before. So essentially estimate the score of this underlying stochastic process, but now purely based on simulations. And if you do this, then already in sort of the first episode, you at least get sort of close to the target. Okay, and then after, or you still get sort of at least going in the right direction. And after about 10 episodes now, it has solved the task. It refines it a little bit further during the next episodes and so on. So it already starts off much better, right? Much more informed by the underlying physics. Even though the model is just a neural network ensemble, right? It's basically just a fully data-driven model. All we do is we sort of regularize it a little bit towards behaving like what the simulator does. So here's some quantitative comparisons. So what this plot shows is negative log likelihood on holdout data set collected on hardware to kind of predict next states, basically, from current status and actions. And we compare, on one hand side, an approach that basically just does system identifications, just fit the model to data on the simulator, and then evaluating that predictive model on the holdout data. Here's kind of the uninformed neural network model, right, that I had discussed before, right, where initially, of course, you start off much worse, but eventually you find better solutions. Another natural thing one can do is to sort of do a gray box model. Where you basically kind of estimate a physics-informed maybe mean, and then sort of learn some deviations from it using neural network. And that already starts off at a better place, but in the event it converges sort of to the same solution. And here's this approach that's fully data-driven and just regularized towards this neural network prior. And not only does it start off at a better spot, but it also converges to a better solution in the end. And here's an experiment of that sort of is a quantitative version of the videos I showed before. The x-axis is the number of episodes to carry out, and the y-axis is basically the achieved performance at the task. And the green one is basically this model-based RL from scratch with an uninformed prior, knowing nothing about physics. And the blue one is basically that sort of regularized towards this bicycle model, right? So it's this very simple first principle model, right? And again, it starts off at a better spot and more quickly sort of finds a good solution. Okay, so that's basically what I wanted to talk about, right? So I think there's a lot of exciting open challenges still to be solved. Then trying to develop agents that can really safely and efficiently learn by interacting with the real world. And I think one of the key challenges in this domain is really enabling models to learn to know what they don't know, right? I think that's also one of the big frontiers currently in sort of foundation models, right? How can one, in a way, figure out kind of the boundary of where the learned representations still are meaningful and where they are not? And I think that's sort of a key challenge to work on. And so one thing I just want to briefly mention, so in Switzerland, our next generation supercomputer in Lugano is coming online in the future, in the near future, with a sizable number of top-of-the-line GPUs. And so we are very much hoping to get a chance to try out some of these ideas and scale them to larger scale settings in this context. So here's just some of the references in case you want to read up more. I guess it's being recorded. And I'd like to end by thanking all the collaborators who I got a chance to work with in this research. Thank the funding agencies, and thank all of you for your attention. Thank you very much.
Thank you for the talk. I'm curious what your thoughts are on maybe an alternative approach in imitation learning. Would you argue that we lose sort of the safety guarantees that you're presenting here, or I'm just curious your take?
No, so imitation. So I think one potential fundamental limitation in imitation learning, of course, you can always only do as well as sort of what you get to see, right? Now, of course, there's various different ways of starting with imitating something, right, and then sort of trying to improve upon that, right? There's various different ways of doing so, and I think that's probably exactly the way to go, right? And in some sense, yeah, I think there's lots of ways of interfacing this, right? So, for example, one can sort of, using imitation learning, try to find an informed sort of latent space and then apply all the methods on kind of that informed latent space as opposed to maybe in kind of a generic state space. So that's one potential way to go. I think there's many other approaches to interface it. I think it's quite complementary. Yeah, please.
Well, like the situation in which you were weighting the learning from the simulator, is it possible to take it to a more granular level, like the action space? Like in the case of the pendulum, we have one action space, right? But in the case of the multi-wheeled robot, each of those motors would represent a separate action space. So is it possible to maybe learn the uncertainty for each of those individual actions that you could take, and then possibly weight them separately, rather than weighting the entire learning from the simulator as a separate?
It's a good question. So basically, so now if you have multiple actions, right? Of course, in principle, you could just sort of feed them into some black box that predicts kind of what's going to happen, right? And apply the approach as is, right? The question is maybe, is there some more fine granular way to go about this?
Right.
And so we're going a little bit in this direction. So one way to sort of think about this in a way is through the lens of sort of causal discovery, right? Where you really try to kind of think about causal effects of individual actions you might apply and how they might, in a localized fashion, affect the state space. And we've been doing some work in sort of model-based causal Bayesian optimization that sort of goes in this direction. I think there's a lot more to do in this space, but thanks a lot for the question. Any other questions? Then let's go for pizza. Okay, yeah, then thank you very much again.